Math 1325, we are up to our final week of the semester. All that's left is the review for the final and the final exam itself. So maybe a good plan for this week, since you have nothing else going on, is to do problems 1 through 10 on Monday, 11 through 20 on Tuesday, 21 through 30 on Wednesday, and that way you break it up into 3 segments that aren't so long. You'll have a good grasp of all 30 problems, and then Thursday and Friday you can take the test one time. So most students will wait till Friday to do it, which means Thursday you could give yourself one final practice run and sit down and like it's an practice exam, and do a 2-hour sitting and run through all 30 questions in one sitting. If you get a good grade doing that, that tells you you're ready for the final that you could do the next day. And if you didn't get a good grade in that one practice run, that's a warning that you're not ready yet and you need more practice. So we're going to review the first 10 problems here in this first video, and then we'll pick up with the next 10 on the video after that. So this is the review for the final exam, and the final is very close to this review. So your best chance to get a good grade on the final is to practice the review as much as possible. Give the domain and range, then use the graph to find f of -2, f of 0, f of 1/2, and any x values such that f of x equals 3. So the beginning of our course, way back in August, was some algebra concepts. So this is all algebra here. There is no calculus anywhere in this problem. But I'm looking at this graph right here. The domain is how far to the left can you travel, and how far to the right can you travel, left or right. And sometimes these are stopping points, like they are right here at the ends, but sometimes they put arrows and they can continue in either direction, either or both. But this one, neither one continues on. So the farthest to the left I can definitely go is right where that closed circle is. And then domain's about the x value. So you come down here, there's a -4x value right there. So the domain, the farthest to the left I can go is bracket -4. And the farthest to the right is when you get down here at this dot, which is right at x equals 2. And you do have closed circles there, so that's why both of these are brackets. Sometimes they put open circles on either one or both of those, then you'd have parentheses for any of those. Similar deal for the range, except range are about y values, and it's how low down can you go and how high up can you go. So if I travel on this little back and forth shape here, the lowest I ever get are these 2 points right down here. So it's okay if there's a tie. So at -2 and at +2 for x's, I have y values of 0 at both of those spots. This coordinate right here is -2, 0. This coordinate is 2, 0. But they have a y value of 0, and the y's never go into the negatives on this graph. So the lowest I can get is exactly 0. And then the highest I reach is this little corner point here, or this closed circle. They're tied for the highest. And they both have a y value of 6. So 0, 6 is the range. F of -2 means what does the y equal when x is -2? And we talked about that one a second ago. When x is -2, the y is exactly 0 there. When x is 0, what does the y value equal? That's right here. The y value is 6 at that spot. And then for 1/2, we might have to estimate this, but here is 2. This would be 1. 1/2 would be about right there. And I'm guessing they wanted to come out exactly, so maybe it doesn't look like that's exactly halfway across, but I would assume they meant it to be. So, because otherwise there's no way to tell. If it wasn't exactly 4, if it was like 4 point something, it would be impossible to tell from the eyeball. So it's a little distorted here, but it looks like it's not exactly halfway in between. It seems like it's a little closer to the 1. So somebody could argue, well, if I go to exactly 1/2, it seems to be a little bit more than 4, but because of that fact, there's no way we could know what it is. So I'm assuming they wanted that to be exactly 4. And it was just a computer programming issue to make it look like it's exactly at 1/2. And then finally, what are the values of x for which f of x equals 3? In other words, if y is 3, what x values happen there? So here's a y of 3, and if you go across, anything on this horizontal line right here is a y value of 3. And you can touch the graph here, or here, or there. You can touch it 3 times. It's okay if the y's repeat. So at -3 with +3, if I'm at -1, I would be at +3. Or if I was at +1, I would be at +3. All 3 of those x values have a y value of 3. So that's just the backwards version of the previous 3. Okay, this is another thing taught in algebra because they know you need it in calculus at some point, but they slowly want to teach you what might be easy for you now is do f of x plus h for part A, then f of x plus h minus f of x for part B, and then do that divided by h for part C. This is building up to the definition of a derivative using the limit. And this is actually everything we do in calculus when we learn the derivative at first, before there's any shortcuts to it, but except for the last step where you do the limit as h approaches 0. So they teach this in algebra classes so that algebra students get used to doing this, and that way when you get to calculus, the calculus part of this is very easy. So number 2, f of x equals 6x squared minus 7x plus 9 part A just wants f of x plus h. So everywhere you see an x, you put an x plus h. Everything else is still there. Still got the 6, you still got the square, you still got the minus 7 and the plus 9. And then we can square this part out, and maybe it's been a while, you don't remember this, but it turns out you square the front term, x squared, you multiply this together and double it, so it becomes 2xh, and then you square the h. And then let me just go ahead and do this all at once. So this will be 6x squared plus 12xh plus 6h squared minus 7x minus 7h plus 9. And it was very common on problems like this to get 6 terms out of all that. There's 6 terms here and they're all different. None of them are like terms that can be combined together. So there's a 6x squared plus 12xh plus 6h squared minus 7x minus 7h plus 9. So that was always our first task, was to get the f of x plus h. Now if you take that and take that f of x plus h and minus the original f of x. So the original f of x were these 3 terms. I'm going to put the minus on each one and get a negative 6x squared, a positive 7x, and a negative 9. And maybe you remember back when I did that, I used to have this like all the way on the right there. It was all in one long line, but it's okay if you don't. If I ran out of room over here, I can't fit it in. But out of the 6 terms that I got for part A, however many terms there were in f of x, there's 3 here, but it could be 1, 2, 3, or whatever. However many terms you have there, once you switch them all to the opposite for this minus part right here, this is what I get from that. all of these terms, no matter how many there are, they should all have opposite counterparts that cancel with some of the ones here. So the negative 6x squared better have a positive 6x squared it cancels with. It does. The positive 7x better have a negative 7x to cancel. And the negative 9 better have a positive 9, yes. So the only thing left is 12xh. 12xh. The 6h squared was left. And the minus 7h. In fact, what happens is anything that has an x in it only has an x in it. Or let me say it this way. Anything that has an h in it doesn't cancel. The three parts that had h, they end up not canceling. Everything else, there was an x squared, there was a 9, there was a 7x, those all canceled. The three that canceled didn't have any h's in them. So now what happens is now you want to divide by h, and that's because all the remaining terms have an h in them. So if I factor out an h from each of the remaining terms, take this h away right here, you'll have 12x left. Take one of these two h's away and you'll get 6h. Take this h away and you'll get a minus 7. Factor that h out, and now the step C is to divide by h because that's what makes this go away. So the algebra answer is this right here, 12x plus 6h minus 7. 12x plus 6h minus 7. This is what algebra says the answer is. When you get these, this is called a difference quotient in algebra. F of x plus h minus f of x all over h. In algebra, they teach this, and a college algebra student, they would just say this is the answer. They don't know any calculus, obviously. There's one calculus step that we're not doing here because this is from the pre-calculus chapter. But when we get to the calculus chapter, the final step actually is the easiest step of them all. You do limit as h approaches 0. And as soon as these h's cancel, you don't have an h in a denominator anymore. You just stick 0 in for that h right there. The 6h disappears, literally. That's all that happens when you plug 0 in. So you just get 12x minus 7. Calculus would say this answer is 12x minus 7. And in fact, you guys know the power rule now. Remember the power rule? 2 times 6 is 12. Decrease the exponent by 1, so x to the first. And then negative 7x, the derivative of that's negative 7, and the derivative of 9 is nothing. So now you guys know a much easier way to do these long derivatives with the power rule. 12x minus 7 is the derivative of this. Although that's not the answer to this problem. It's part of the answer, but it's not the whole answer. So here you can't really do that shortcut to get this answer, but later when they ask me to find the derivative of this using the limit idea, then I don't have to go through all that if I don't want to now. I could just do the shortcut at that point. Okay, another thing from algebra is to use completing the square to set this up into a nicer format. And that way you can see the vertex of the parabola. And this is slightly different than doing completing the square in an equation where it could be equal to 0. So the issue here is I have s of x. This isn't equal to 0, and I got to leave that there the whole time. So I got to work entirely on the right side of the equation. And minus 27. And you can't do completing the square unless you have a 1x squared. This negative 2 is kind of messing us up as well. So I'm going to factor out the negative 2. It's easy on the first term. You just literally split these two things apart right here. But it affects the second term. Negative 16x divided by negative 2 is positive 8. And then you put a plus blank. This is the process of completing the square right here. In other problems where it's not equal to f of x or whatever over here, if you just have an equation where it's equal to 0, then you can add this 27 to the other side of the equation and get it out of the way. But here we can't. We have to leave it here. You just put it outside the parenthesis because it's kind of in our way and we don't need it. But we can't just get rid of it because we don't like it. And then this plus blank here is going to get balanced with another blank. When you're doing them both on the same side or on opposite sides of the equation, you put plus blank on both sides. But when it's on the same side, they're in essence going to be opposites of each other so that you're adding and subtracting the same amount and not changing what you have. Although we can't immediately tell if it's going to be plus or minus right here. Okay, so bring down the -2. The process of completing the square always creates an x something squared. That's the whole point of it. And the something is half of that +8 right there. Half of +8 is +4. +4 squared is 16. That's the process of completing the square. And when you first learn it in algebra class, there wouldn't be a -2 here, and we would have this 27 on the other side of the equation. So then you would put +16 here, and you'd put another +16 over there. So this is where it gets a little different. So I'm doing it all on this side of the equation. So +16, you might think that you need to put a -16 right here, but this +16 is affected by this times -2. The same way this 8 is not really an 8. This 8 is a -16. This 16 is really a -32. So you have to multiply whatever you put in this blank times any number that's in front. Whatever that product is, you put the opposite right here. So the opposite of -32 is +32. And that keeps the equation in balance. So -27 plus 32, these two numbers right here add up to +5. So now I have the vertex form of a parabola, which is a times x minus h squared plus k. That's the format we were trying to put it in, and completing the square is the only way to do that. And then things that this tells you is A tells you two things. It tells you if the graph opens up or down. This would open down because it's a -A. This is a parabola that opens down. And the 2 makes it a vertical stretching too, so it's real thin because of that. And then the vertex is the coordinate HK. But notice in the format there's a -h right here. That means it's always the opposite of the way it looks. So if -h is +4, well, that means +h is -4. But the k stays the same, +5. So this, I think they only want the vertex for this answer. That's it right there. But if you were graphing this, you would have a -4, +5 vertex. The graph would open downward, and it would be thinner than normal because of the 2. In fact, if you went 1 unit to the right or left of the vertex, it would go down 2 instead of the usual up 1. So they want the format first, -2, x plus 4 squared plus 5, and then the vertex is -4, 5. Check -2x plus 4 squared plus 5. So on this review again, you don't get to check the answers till you're done. So I'll submit them after every 10 problems and see how we do on each 10. But one time you need to be able to do as much of it as possible in one sitting and submit it and get a good grade. Once you have a good grade on this, or anytime you get a good grade on it, then any other time you do it, the grades don't matter. Only the highest grade counts. So if you do like my suggestion and do the first 10 on Monday, the next 10 on Tuesday, the next 10 on Wednesday, you're going to get bad grades on all 3 of those, and that's okay. You can submit them and have it graded just so you can see how you're doing. And then if you have one final practice run later where you do all 30 problems, and if you get a good grade on that, that's the only grade that's going to matter. And as soon as you have a grade you're happy with, you can do any amount of it at all. You could even just do one problem and submit it, and even though you'll get a bad grade that time, the highest grade is the only one that counts. Okay, next thing we'll need to talk about to review is what's called end behavior. Polynomial graphs always shoot up or down at the ends of the graph. So when you are way off to the left or right, they're either shooting upward or downward. And they can both be up, both be down, or one of each. Anything like that can happen. But so near the middle of the graph, there's a lot of waviness of ups and downs, or sometimes it just one time it goes back up again. But there can be a lot of waviness of ups and downs in the middle of the graph, but at the end, things settle down. When x values get very, very large, then the y values either get very, very large up to infinity or very, very low down to negative infinity. When you're closer to zero, then different things can happen. So somebody noticed that all polynomial graphs do that at the far right and the far left. They're either shooting way up or way down every single time. So there's really 4 cases to know, but all I do is I just memorize the 2 easy graphs that we already have memorized. Everybody that's in this class should know that an x squared graph looks like that. And an x cubed graph, cubic function, looks like this. And this one has an even degree with a positive leading coefficient. This one's an odd degree with a positive. So I remember these 2 positive examples because they're ones we already have memorized. We can picture these in our mind whenever we're doing them. So anytime you get a positive even, the end behavior, it's up on the left and up on the right, or rises on the left, rises on the right, or sometimes they say as x goes to negative infinity, what does y do? And you say it goes up to positive infinity, things like that. So positive evens, they're both up. And then if you get a negative even, you just do them backwards. A negative even, they're both down. Opposite of what happens when it's a positive even. If you get a positive odd, it's down on the left and up on the right. So if you get a negative odd, they just are both backwards. It's up on the left and down on the right. So this is a negative even because you have to make sure it's in order though. First, the x to the 4th is the highest exponent. This is a polynomial. This is in polynomial format, and it has a 4 for the highest exponent. That's an even degree. And it's got a negative leading coefficient. So this is a negative even. Well, positive evens, they're both up. So it's not that one. And it can't be the one where it's one of each. That only happens on odds. It can't be this one. That's another positive even. It's definitely this graph without knowing anything else. This is the only graph where both of the end behaviors are going downward. That's what happens with a negative odd. I said that wrong. Negative even. Negative even, they're both down. Definitely. So these 3 graphs are impossible just because the end behavior is wrong. And normally, graphing these things can be very hard. If you didn't have multiple choice here, all I would know at this point is they're both down. In college algebra, they teach students an entire chapter of, which gets really hard at times, of where do these graphs cross the x-axis or touch it? And then maybe things like the y-intercept too, or how many times does it change directions? When does it increase? When does it decrease? All of that stuff, you could spend entire weeks of a class learning all that little detail, but luckily here it's just all about the end behavior only. So another thing too that you can tell from these graphs, first of all, there I can see the end behavior here. It's up on the left and down on the right. So that's definitely an odd degree when they're opposite. And this is the opposite of the one we have memorized, so this makes it's a negative odd degree. Has to be an odd degree. So it cannot be choice A where the degree is 8, 10, or 12. That's impossible because that's even. Even, they would both be ending in the same place, which it's not here. It can't even be 5, 6, or 7 because of the 6 is impossible. So it could be 7, 9, or 11, or maybe you can't determine it. But if you see a graph, you should be able to determine it. So apparently the answer is going to be B. So one way to tell this is how many times does it touch or cross the x-axis and how many times does it change directions? So I've got a cross point right there for 1, and it's decreasing all the way till there, then it increases. So the number of times you touch or cross the x-axis, that's the minimum that your degree could be. and the number of times it changes directions is 1 less than the degree that it could be. So if the smallest possible degree is 7, apparently just based on multiple choice, that means I should cross or touch the x-axis at least 7 times, and there should be 6 turning points, they call them. So I'm changing directions right there. That's 1. There's a second x touching point or crossing point. 2, there's a change of direction right there, what we call local maximum in calculus. Then it goes and touches the x-axis for a 3rd time right there. Then it has another local minimum, that's a 3rd turning point. Crosses the x-axis for a 4th time. Then it's got a local maximum, another turning point for the 4th time. Another x-axis spot for the 5th time. Another local minimum for the 5th time. An x-axis crossing 6. There's a 6th change of direction, and then there's the 7th crossing or touching the x-axis. In fact, it crosses all 7 times. It doesn't just touch it. So it crosses the x-axis 7 times, and it changes direction 6 times, which are local maxes and mins for us in calculus. So it has to have at least a 7 degree. It could be higher, because when you cross through, you could have a degree of 1, 3, or 5 at those spots. So from the graph alone, you can't tell if it crosses through, is that a 1, is that a 3, is that a 5? But it's at least a 1. So this has at least a 7 degree, and it could be any odd number higher than that too if you have multiple multiplicities here. So yeah, the answer is definitely B for that part. And the sign of the leading coefficient is definitely negative because of the end behavior. I knew that from the end behavior already. Okay, another thing we do in algebra is solve exponential and log equations. So number 6, this is kind of the ideal case to get. Actually, this is what I would consider level 2. There's 3 levels of these solving exponential equations. The first level is the easiest level. That's when you're able to make the bases the same by changing the bigger one to look like the smaller one. So let me give you a smaller example. Say you had 9 to the x equals 3 to the 4th. It's making something up here, but say this was your 2 bases, 9 and 3. It's possible to make 9 look like a 3 because 9 is 3 squared. And then you have the rule of exponents where you multiply the exponents. So 2 times x is literally 2x. And you make the bases the same and they cross out after you have the exponents settled. And then you solve for x. This is the easiest kind because I'm able to make the bigger number look like the smaller base. The bigger base can turn into the smaller base pretty easily. But there's no power of 16 that 64 is equal to. 16 to the first is 16, and 16 squared is 256. So there's no way I can make 64 look like a 16 the way I made 9 look like a 3. But 64 and 16, they can both go down to a smaller base. They're both powers of 4. 16 is 4 squared. And 64 turns out to be 4 cubed. And then the third level, which luckily we don't have here, but there's a third level where say that 16 was a 15 or the 64 was a 63. Then you can't make the bases the same no matter what you do. So then what you have to do is you have to multiply both sides, or you insert a log on each side of the equation is what you end up doing. And the property, maybe we'll see one of those in the review later, but then the property of logs lets you bring the exponents down is how you get unstuck at that point. But here I'm able to make the bases the same, so they're both going to be 4s. But I want to use the rule of exponents first to settle these exponents. So I need to multiply this. 3 times 3x is 9x. And then here when you multiply, you're going to distribute and get 2x plus 6. Once your exponents are situated, then you can cross out the bases. So then you're left with a pretty easy algebra problem to solve. And they often don't come out exactly because they don't want people guessing and checking. So minus 2x, this is not going to divide evenly, but that's okay. 7x equals 6. divide by 7, x equals 6/7. And you always get an answer here. This can never be undefined or no solution because the domain of exponential is infinite. But when you solve log equations, then sometimes the answer is no solution because their domains are not infinite. So here's a log equation right here. Log base 3 of 3x minus 4 equals 1. This kind of has a 3 levels as well. So this was kind of the medium. This one right here is the medium level of exponentials. This is the easy kind. And then there's a hard kind where, as I described, where you can't make the bases the same. A similar thing happens with log equations. The easy kind is when there's one log on each side of the equation and nothing else. So I have log base 3 of 3x minus 4. If the other side of the equation was log base 3 of whatever, then I could just cross the logs out. But the other side here doesn't have a log in it. It just has a 1. So the easy kind would have been log base 3 on the left, log base 3 on the right, cross out the logs and solve the equation. The medium kind is this, where there's one log only on one side of the equation. And the other side is just like a constant. The hard kind is when not only is there a log on each side, but then there's an extra constant attached. Like if I put 1 plus or minus some other log, then it's a really hard problem actually. Harder than what this one is. So at least you got the medium kind for both 6 and 7. For the medium kind here, the only thing we can do is take this log form. I can transform it to its equivalent exponential form. There's a whole bunch of homework problems where you do that, where you just translate them back and forth. So I circle these 3 parts of this log right here. And I say to myself, which of these 3 things is a base? We read this log base 3. So most people know that's the base. In a log, the base is the down low number. In an exponent, the base is the regular size number. And then I say to myself, a log is an exponent. A log is an exponent. This is why the rules of exponents work for them. And this is why the properties of logs are all resemble the properties of exponents. A log is an exponent. I just say that to myself a few times. A log is an exponent. A log is means equals in math. A log is an exponent. There's your exponent over there. And we all know that that's the one that goes up high over here. The exponent is the raised up number. And then the only thing I haven't used yet is this domain part of the log, so that's what this is equal to. There's 3 parts of a log form, there's 3 parts of an exponential form. It's all about where does the base go, where does the exponent go, and then whatever you have left over is what has to go in the last slot. And then you get problems in the homework where they give you this form and they want you to write it as a log, and you just do it backwards. Well, now I can finish this problem because the log disappears basically. 3 to the first is the same thing as 3. I'm just solving an Algebra 1 high school problem now. Add 4. That's going to be 7 equals 3x. And divide by 3. X is 7/3. Okay, now we start hitting some actual calculus stuff. That was the end of the review of algebra chapter. So the review has 30 questions, and I went back and counted. We did about 26 or 27 sections total. I can't remember what it was exactly, but if you go right here and count all the blue sections, well, one way to tell is there's 6 here, and all the other ones had 7, so 7, 14, 21 plus 6, there's 27 sections. 27 sections. We had 27 sections of homework. So I picked 1 problem from each section. That's 27, and then a few sections got 2 problems. Like a good example where 2 would be the section that had the product rule and the quotient rule. Then I picked 1 of each of those. So that's where the 30 problems came from. So you're kind of getting like the most basic important topic of each section. So one thing that can make this final a little more doable than you might think, yeah, unfortunately you have to know the whole course in one test, but it's just basically the most major important problem from each section. You don't get all the weird ones and the exceptional cases and where the little mistakes are made as much. So there's definitely a chance to get a good grade on the final, especially if you practice this review. So first thing we learned in, whoops, where am I over here? Well, this actually wasn't the first thing. The first thing we learned in limits was to do it with the table method or the graphing method. And you could do that in general for problems like this. But then here's where things got shorter and easier, was some limits can be solved with properties. So this was right after we learned how limits work with graphs and tables. And then we discovered some of them have shortcuts to them. One thing that can help in a limit is, well, first of all, the first idea is always see if you can just plug this number in. If you can plug this number into a limit, it's usually going to be the answer. That's the rule for polynomials. That's the rule for rational functions, as long as it doesn't make the denominator 0. But unfortunately, plugging 7 into this function would make the denominator 0. So then I can't just plug it in. So instead, we have to employ some kind of trick or strategy or property. And the strategy that helps here is that the numerator can factor. If you can factor and cancel a rational function, you get similar answers, actually. It's just that the part that you're losing still affects the problem, but at least it goes away in terms of finding a limit. So I can factor this numerator. In fact, you don't have to even think too hard because it's probably got this in it. Hopefully it does. That's the only way to get unstuck here. So what I could do is this and say, okay, hopefully there's an x minus 7 there. So that way that'll cancel with my denominator. And then I'll be able to plug 7 in because there won't be a 7 in the denominator anymore. And if the last sign is negative, you got to have one of each. I already have the minus here, so this has to be a plus. 7 times 4 is how I would get 28 if it's going to work. And notice that negative 7x plus 4x does make negative 3x. So you just have to double check that real quick. So yeah, it works. Now, if this 28 was a 27, then I wouldn't be able to do this method that I'm doing right now. So they intentionally made this problem come out nicely, but now the x minus 7's cancel. So if you were doing still the algebra side of this problem, remember asymptotes, normally there would be a vertical asymptote at x equals 7 because it makes the bottom 0, but not if it reduces with the numerator first. So we're losing our vertical asymptote if we were doing the graph of this problem. But that 7, it doesn't just disappear entirely. The domain still cannot have 7 in it. It turns into a hole in the graph, actually. All that's left is a linear function right here. So if you just graphed a line that had a y-intercept of 4 and a slope of 1, you would just have a line like that, except when you got to 7, there'd be a hole in its graph. So it isn't like the 7 completely goes away from existence, but it does go away in terms of the limit. So now I don't have an issue plugging this 7 in anymore. 7 plus 4 is 11. But what would happen on the graph is you'd have a y-intercept of 4. You'd go up 1 over 1 7 times. 2, 3, 4, 5, 6, 7. Right there, there'd be a hole in the graph. This would be a line with a hole in the graph at 7. And in fact, if you use the graphing method for limits, if you go a little bit to the left of 7, like 6.99999, you would touch right there below the circle, and that would turn out to be just slightly less than 11. And then if you go a little bit to the right of 7, 7.001, that would be a little bit above that circle, be a little bit above 11. And that would be another way to see that this answer is 11, actually. Or if you did the table method with a graphing calculator, you would get like 10.99 for the left side and 11.01 for the right side. And that's another way to say the answer is 11. So 3 different ways that problem could be done. But on a test, it doesn't matter which one you do, but the easiest way is factoring and canceling. Okay, piecewise functions are good when you learn limits because there's a chance that these separate pieces could be separated or connected together. They sometimes connect up with each other. So then if they're separated, it causes you to get an issue for a limit. Your left-sided limit can disagree with the right-sided limit, causing there to be no limit. The limit does not exist, we say. But if they connect up, then you can get not only a limit answer, but also a function answer. Although you can get a function answer on these two, even though there's no limit to them. Okay, so the graph is 11, horizontal line of 11, anytime x is less than -1, which is that segment is correct right there. And it's got just less than -1, so that is an open circle right there. This graph is wrong because in order for that to be a closed circle right there would have to be a line under this less than right here. Now, this could still be the answer because there could be a hole right here that gets plugged up by the other piece landing right on top of it. So all I've eliminated is graph B so far. You're also a horizontal line of 11 anytime x is greater than 3, which is that or that. So I can't eliminate either one. There could be an open circle there. There could be a connection up. So it all depends what this graph is doing at those two spots. So the easiest way to do this is plug in -1 and 3, those two limits right there. Plug those in here and see what y values you're getting. Really all we care about is, are we getting this 11 here or this 11 down here? So -1 squared is +1. +1 plus 2 is 3. So it's definitely not this graph. It's down here at 3. And there is a line under that, so that is a closed circle there. When I plug 3 in, though, 3 squared is 9. 9 plus 2 is 11. So there should be a closed circle right here. And then this piece has an open circle. But when an open circle lands on a closed circle, then it just connects up like this, and we don't put any circles. So this graph C is wrong for two reasons. The main reason it's wrong is this does not connect up over here. There is a gap right there like that. Plus, even if it did connect up there, if it connects up here, you don't put the open circle anymore. That would be misleading. So if you ever see that, you can tell that's definitely wrong. They would never do that. If this equals 11 and plugging 3 in gives you 11 here, the two pieces connect up and it's continuous there. And you wouldn't even notice that it was separated at any point. And then we could actually connect this piece up right down here. If you change this 11 to a 3, then this would be connected up too. But since it's 11, it's not connected to it. So there's the correct graph. And it's discontinuous in one spot only. It's only discontinuous at an x value of -1. And then we want to do the limit at any discontinuous spot. So a little bit to the left of -1, you're up here at 11. A little bit at the right of -1, you're down here at 3. So the left-sided limit is 11. The right-sided limit is 3. Since those disagree with each other, that's why there is no overall limit, although they're not asking for that here. So I guess they're just saying, okay, if it's discontinuous at a spot, it's not going to have a limit there. So therefore, just tell us why it doesn't, because the left-sided limit is 11. The right-sided limit is 3. Now you're showing why there's no limit there. The two one-sided limits do not agree with each other. The only way to get an overall limit at any given spot is you have to have the left and the right-sided limits agree with each other. Any kind of disagreement, then it's definitely that there is no limit there. The function exists there. There's a closed circle exactly at 3. So f of -1 actually equals 3. But the limit doesn't exist there. Okay, final question for this first video. Find the instantaneous rate of change for the function at the given value. So let me show you what was meant to be done here just to review this. And then I'll show you how you could do this a whole lot easier. F of x is x squared plus 3x at x equals -4. Here's how we learned it back then. This is the other half of that problem. Limit as h approaches 0 of the difference quotient. F of x plus h minus f of x all over h. So we can repeat what we did on that problem towards the beginning of this review. So plug in x plus h into these two x's right here. So here you'll see it all in one long line because back there I kind of ran out of room doing it part by part. So I like to put a bracket for the f of x plus h. X plus h goes here. Plus 3 times x plus h. And then we do minus f of x, just rewrite it as it is, all over h. So this part right here, the squared part, is, let me write this again, limit as h approaches 0, x squared plus 2xh plus h squared. That's the squared part, those three terms. And then we get a 3x and a 3h. There's only 5 terms here instead of 6 because there's no like plus or minus anything at the end here. And there's only 2 terms here. So when I put the negative on these 2 terms and switch them to their opposites, these 2 should have counterparts that cancel with them. All over h. All the remaining terms have an h in them, so I can factor an h out. Take this h away, you'll have 2x. Take one of these 2 h's away, you'll just have an h. Take this h away, you'll just have a plus 3. Now finally the h here cancels this h, which was causing the problem. I couldn't plug 0 in because of that. But now I can plug 0 in, just like that factoring problem we had a minute ago. So we're left with, where am I here? 2x, I couldn't read that at first, 2x plus 3. Now remember, algebra would say this whole thing here is the answer. Algebra would say the answer is 2x plus h plus 3. Calculus would say the answer is 2x plus 3 because the h would go to 0. This is f prime of x. And you probably knew this a whole lot more easily if you had just used the power rule. You could have avoided all this mess. I just wanted to review it for you one more time by doing the power rule. The derivative of x squared is 2x. The derivative of 3x is 3. So that you could just do that on the final and just say, I already know what the derivative is. An instantaneous rate of change literally means derivative. So at this exact moment in time, what does the derivative equal when x is -4? Plug -4 into the derivative function. -8 plus 3 is -5. So that would be the slope of a tangent line at this graph. If you drew this graph would be a parabola, x squared plus 3x. If you had an x equals -4, say that's right there, the tangent line would have a negative slope to it, exactly at that spot. Exactly at this spot, there's a slope of -5, and that makes sense for this graph right there that it's going down 5 over 1. So that's what instantaneous rate of change is all about. It's just the derivative evaluated at that one given spot. The derivative evaluated at -4 is -5. In other words, the slope of the tangent line at that spot of the graph is -5. And so this problem could be easy on the final if you just use the power rule to get the derivative and then plug the x in. But this is where it came from. This tries to show you where the power rule actually came from. Okay, so we've done 10 of the 30 problems, and it took me about 50 minutes to get here. So if you do 50 minutes times 3, we're talking well over 2 hours. So rather than one video that's over 2 hours long, that's why I'm breaking this up into 3 videos. Hopefully each is around about an hour or a little less. So that way it'll take you about 2.5 hours to get through the video. And if you were doing the review or the test yourself, you get 2 hours for the test, but it takes me longer to do problems because I'm explaining everything and writing things down slowly on this whiteboard. So you should have enough time to do all the whole thing in 2 hours when you actually take the final. So I'm going to submit this now, and if I get 10 out of 30, 33%, then that means I got a maximum grade so far. And then if I was trying to get a grade for a homework, unfortunately, I would need to do it again and get a higher grade than 33, but that's okay since I'm not doing it for homework. Okay, I didn't get a 33, I got a 29. So what happened here on number 1? Okay, so I was wrong about that. But see, this is good that you guys saw me mess it up before you do it. Remember how I said that I assumed that it should be 4 just because how else are you going to know that? So in my opinion, that's still hard to tell. How would you know that that's exactly 4.5? That's hard to tell. But when x is a half, it seemed like it wasn't there exactly to me, but I didn't think, how would you know that that's exactly 4.5? That's a little hard to tell that that's exactly that, but apparently that's what they want you to do there. So sometimes you have to get them wrong before you can tell what they wanted exactly. I thought it was a mistake by the computer, that it was just getting this graph off slightly, but actually they did that on purpose actually. So that they meant that to be 4.5. Now, how can you tell exactly? Yeah, that's a little vague in my opinion, but we got to do what they got here. So that's the only thing I did wrong on number 1. But if you notice that when you do your review, then you can get saved and get that point. And what did I do wrong here? 6/7. That's weird. Oh, wait a minute. Did I make the mistake of writing the problem down wrong? 3x and x plus 2. Let me check that. Maybe I couldn't even read my own handwriting at that point. 3x, x plus 2. 9x. Oh yeah, look, I switched to a 3 here somehow. My 2 became a 3, so I had a brain cramp type of mistake. This was supposed to be 4, not 6. So yeah, that's the only thing I did wrong there. But I lost the whole credit for the problem because of a brain cramp mistake. So yeah, be careful on things like that, both in your review and especially on your final. Unfortunately, I make mistakes like that too. And once you make mistakes like that, it costs you points. I only got, where did it go? It's not there, okay. So, well, oh, it's right up here, 29. So that cost me 3.5 percentage points by making those 2 minor mistakes. Well, one was because I didn't realize what they wanted, and this one was just a brain cramp mistake. But at least what I showed you is true. All the steps that I showed you were true. So we'll pick up with 11 through 20 in the next video.